Picture this. You're in a dark laboratory. The only sound is a low, steady hum, barely audible, somewhere around middle C on a piano. In front of you sits a flask of water, completely ordinary water, sitting perfectly still. And then, a flash. A tiny point of light, no bigger than the head of a pin, suddenly appears in the center of the flask. It pulses in rhythm with that hum, appearing and disappearing thousands of times per second. Blink, blink, blink. Like a captive star, breathing in the darkness. This isn't magic. This isn't CGI. This is real. And it's one of the most bizarre phenomena in all of physics. Welcome to the world of sonoluminescence, where sound creates light, where a humble bubble in water becomes hot enough to rival the surface of the sun, where the laws of physics do things that still make scientists scratch their heads in wonder and confusion. Today, we're going down the rabbit hole, and trust me, it gets weird. The discovery. Let's rewind to 1934, the University of Cologne in Germany. Two scientists, H. Frenzel and H. Schultes, are working on something completely unrelated to mysterious glowing bubbles. They're studying how to speed up photographic development using ultrasound waves. Practical stuff. The kind of research that doesn't usually make headlines. But then they notice something strange. When they blast their developing solution with high-frequency sound waves, the liquid starts to glow. Just slightly. Just enough to fog their photographic plates. At first, they probably thought they'd contaminated something, made a mistake. But the effect kept happening. Reliable, repeatable, impossible to ignore. They had stumbled onto something that would puzzle physicists for the next 90 years. But here's the thing. After that initial discovery, sonoluminescence basically disappeared. Lost in the chaos of World War II, buried under more urgent research, forgotten in dusty journal archives. For decades, it was a footnote, a curiosity. Something weird that happened once and didn't seem to matter. Until 1989. That's when Felipe Gaitan, a graduate student at the University of Mississippi, was working with acoustic levitation. He was trying to trap a single bubble in water using sound waves. Just one bubble, held perfectly still in the center of a flask by carefully tuned ultrasound. And when he finally managed it, when he got that bubble to sit there, stable and perfect, he turned off the lights, and the bubble was glowing. Not just occasionally, not randomly, but with every single pulse of the sound wave, this tiny bubble, less than 1/100th of a millimeter across, was emitting a flash of light, thousands of times per second, regular as clockwork. Gaitan thought he was losing his mind. He checked everything, his equipment, his water, his eyes. But the effect was real. He'd discovered what we now call single-bubble sonoluminescence, and unlike the multi-bubble chaos of the original discovery, this was clean, controlled, reproducible, and it opened the door to one of physics' deepest mysteries, how it works, sort of. So what's actually happening here? How does sound, vibrations in air or water, create light? Let's start with sound itself. When you play a note on a speaker, you're creating pressure waves. The speaker pushes forward, compressing the air in front of it. Then it pulls back, creating a region of low pressure. Forward, back, forward, back. That's all sound is, pressure waves propagating through a medium. Now imagine those pressure waves traveling through water. Water is mostly incompressible, but it does respond to pressure changes. When a low-pressure region passes through, something interesting can happen. If the pressure drops low enough, the water can literally tear itself apart. Dissolved gases come out of solution, tiny imperfections in the water expand. and suddenly you have a bubble. This is called cavitation, and it happens all the time, in ship propellers, in breaking waves, in your knuckles when you crack them. Usually it's destructive. Those collapsing bubbles can eat away at metal, destroy machinery, and make a hell of a noise. But in sonoluminescence, we're doing something more controlled. We take a flask of water, degassed water, carefully cleaned of impurities, and we put an ultrasonic speaker on one side and a receiver on the other. We tune the frequency just right, usually around 20 to 40 kilohertz, well above what humans can hear. And we adjust everything so that the sound waves create a standing wave pattern in the flask, a three-dimensional acoustic trap, right in the center. Now we inject a tiny bubble, and if we're lucky, if everything is perfectly aligned, that bubble gets caught in the trap. And here's where it gets wild. As the sound wave oscillates, the bubble oscillates with it. During the low-pressure phase, the bubble expands. It can grow to 10, 20, even 30 times its original size. It's like watching a balloon inflate in super slow motion, except it's happening thousands of times per second. Then comes the high-pressure phase. The bubble collapses, and not gradually, violently. The surrounding water rushes inward at speeds approaching the speed of sound in water. The bubble shrinks down to maybe 1/10 of its original size in less than a microsecond. All the energy of that collapse, all that kinetic energy from the rushing water, gets focused into an impossibly tiny space. The gas inside the bubble gets compressed, heated, and for the briefest instant, maybe a few picoseconds, a few trillionths of a second, the temperature inside that bubble spikes. How hot? Conservative estimates put it at around 10,000 degrees Celsius. That's hotter than the surface of the sun. Some scientists think it might reach tens of thousands of degrees, maybe even higher, all from a bubble smaller than a grain of sand. And at those temperatures, the gas inside the bubble emits light. Not infrared light, not red light, but blue-white light, ultraviolet light. The kind of light you only get from extremely hot things. That's sonoluminescence, sound creating motion, motion creating compression, compression creating heat, heat creating light. Simple, right? Wrong. Because we've only scratched the surface. The mystery deepens. Here's where things get properly strange. That flash of light, it's short. Really short. When scientists finally managed to measure it accurately, they found that each flash lasts less than 50 picoseconds. That's 50 trillionths of a second. For comparison, light only travels about 15 millimeters in that time. It's so fast that it's actually shorter than the period of the light wave itself, in some cases. Think about that. The light is being emitted for less time than it takes the light to complete one oscillation. That shouldn't even be possible, according to classical physics. And then there's the spectrum. When you heat something up, it glows with a specific spectrum of colors, depending on its temperature. This is called blackbody radiation. The sun, for example, emits a specific spectrum that tells us its surface temperature is about 5,500 degrees Celsius. It's one of the most reliable relationships in physics. But sonoluminescence doesn't play by those rules. The spectrum of light from a collapsing bubble is weird. It peaks in the ultraviolet range, which suggests incredibly high temperatures. But it doesn't have the smooth, characteristic shape of blackbody radiation. Instead, it has features, structure, specific wavelengths that are brighter or dimmer than they should be. Why? Nobody knows for sure. Some scientists think it might be related to the type of gas in the bubble. Different gases produce slightly different spectra. Argon bubbles glow brighter than air bubbles. Helium bubbles barely glow at all. But xenon bubbles are the champions. They produce the brightest, most consistent light. This suggests that something about the atomic structure of the gas matters. Maybe it's not just heat. Maybe there's chemistry happening in there. Plasma physics, ionization, excited atoms cascading down energy levels, each transition releasing a photon of light. Or maybe, and this is where it gets really speculative, maybe there's something else going on entirely. The wild theories. Over the years, scientists have proposed some absolutely bonkers explanations for sonoluminescence. I'm talking theories that sound like science fiction, theories that push the boundaries of known physics. Let me run through a few. Theory 1, shock waves. Some researchers think that the collapsing bubble creates a shock wave, a supersonic compression front that heats the gas to enormous temperatures, almost instantaneously. This would explain the extreme heat and the rapid light emission. But shock waves should create specific acoustic signatures, and those haven't been detected, so maybe not. Theory 2, quantum vacuum radiation. Now we're getting spicy. In quantum field theory, even empty space isn't truly empty. It's full of virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally these particles exist for such a short time that they don't affect anything. They're just part of the background noise of reality. But what if, during the collapse of a sonoluminescence bubble, the vacuum inside gets disturbed? What if the rapid acceleration of the bubble wall creates conditions where those virtual particles become real, and when they annihilate, they release light? It sounds insane, and there's very little evidence for it. But it's not completely impossible. The energy densities and time scales involved are in the right ballpark. And if it's true, it would mean that every time a bubble collapses, we're literally ripping particles out of the quantum vacuum. We'd be creating matter and energy from nothing. Theory 3. Nuclear fusion, okay. Now we're really in the deep end. In 2002, a team of scientists published a paper claiming that they'd detected neutrons coming from collapsing bubbles. Neutrons, the kind you only get from nuclear reactions. They suggested that the temperatures inside the bubble might be high enough, not just thousands of degrees, but millions of degrees, to cause deuterium nuclei to fuse together. This would be sonofusion, tabletop nuclear fusion, powered by sound waves. The scientific community went nuts. If true, it would revolutionize energy production. But when other labs tried to replicate the results, most couldn't. Some detected neutrons, but way fewer than expected. Others detected nothing at all. The debate raged for years. Most physicists now think that the original neutron detection was probably a mistake. Background radiation, experimental error, not actual fusion. But the fact that it was even considered seriously tells you how extreme the conditions inside these bubbles really are. The current understanding. So where do we stand today? What do we actually know about sonoluminescence? We know the basics. Sound waves create pressure oscillations. Those oscillations cause bubbles to collapse violently. That collapse heats the gas inside to thousands or tens of thousands of degrees. That heat causes light emission? Simple enough. But the details, still murky. The current consensus is that sonoluminescence is probably a form of thermal emission, essentially blackbody radiation from extremely hot gas. But it's modified by the specific properties of the gas, by plasma effects, by the rapid time scales involved. It's not one thing. It's a whole mess of physics happening simultaneously. The temperature inside the bubble during collapse is probably somewhere between 10,000 and 50,000 degrees Celsius, hot enough to ionize the gas, creating a plasma, hot enough to break apart molecules and excite atoms to high-energy states. And when those atoms relax, they emit light. The reason the spectrum looks weird is probably because we're not just seeing thermal radiation. We're also seeing spectral lines from specific atomic transitions, argon atoms dropping from one energy level to another, xenon atoms recombining after being ionized. Each of those transitions produces light at a specific wavelength, which adds features to the spectrum. And the reason the flashes are so short, that's probably just how long the bubble stays hot. As soon as the collapse ends, the surrounding water rushes back in, quenching the heat almost instantly. The bubble rebounds, expands again, and the cycle repeats. It's elegant, it's beautiful, and it mostly makes sense. But there are still unanswered questions, still anomalies in the data, still things that don't quite fit. For example, the light emission sometimes starts before the bubble reaches its minimum size. How? Why? Nobody knows. And some experiments have shown that the intensity of the light can vary randomly, even when all the conditions are kept constant, as if the bubble has moods, as if there's some chaotic element we don't understand. Nature, it seems, still has a few secrets. Why it matters. At this point, you might be wondering, okay, this is all very cool and mysterious, but does it actually matter? Is sonoluminescence just a laboratory curiosity, or does it have real-world applications? Fair question, and the answer is both. First, let's talk about understanding. Sonoluminescence is a window into extreme conditions. It lets us study plasma physics, shock waves, and rapid energy transfer in a controlled, repeatable way. The same physics that happens inside a collapsing bubble also happens in supernova explosions, in nuclear weapons, in inertial confinement fusion reactors. By understanding sonoluminescence, we gain insights into those larger, more complex systems. It's like having a miniature star in a flask, a laboratory universe where the rules are the same, but the scale is manageable. Second, there are potential practical applications. Chemical engineers have explored using cavitation and sonoluminescence to drive chemical reactions. The extreme temperatures and pressures inside collapsing bubbles can break molecular bonds that are normally very stable. This could lead to new ways of synthesizing materials, breaking down pollutants, or even treating diseases. Some researchers have investigated using focused ultrasound and cavitation for cancer treatment. The idea is to create bubbles inside tumor tissue and collapse them, destroying the cancer cells with heat and mechanical stress. It's still experimental, but promising. And then there's the wild dream of sonofusion. Even though the original claims have been largely debunked, the idea hasn't completely died. If we could find a way to create the right conditions, maybe with different geometries, different fluids, different frequencies, could we actually achieve fusion through acoustic cavitation? Could we create energy from sound? Probably not. The physics seems to say no. But then again, the physics of sonoluminescence seemed impossible for a long time, too. Seeing it for yourself. Here's the thing about sonoluminescence. It's not just theoretical. It's not something that only happens in billion-dollar research facilities. With a few $100s worth of equipment and some patience, you can actually create it in your garage. People have done it. Amateur scientists, hobbyists, curious tinkerers. There are YouTube videos showing homemade setups, flask of water, ultrasonic transducer, function generator, some trial and error to find the right frequency, and then, in a dark room, that tiny point of light appears. It's mesmerizing. People who've seen it in person describe it as almost hypnotic, that rhythmic pulse, that captive star, blinking in and out of existence thousands of times per second. It's beautiful, it's strange, and it's real. Of course, getting it stable is the hard part. The bubble is fragile. Any dust particle, any vibration, any tiny imperfection in the water, and it pops. Gone. You have to start over. Professional researchers sometimes spend hours getting everything just right, achieving that perfect acoustic trap. But when it works, when you finally see that steady pulse of light, when you realize you're watching sound create something that looks like magic, but is actually physics at its most extreme, that's special. So here we are. We've traveled from a chance observation in a German laboratory 90 years ago to the cutting edge of modern physics. We've seen how sound can create light, how a humble bubble can become hotter than the sun, and how something so small can contain so many mysteries. Sonoluminescence reminds us that the universe is full of surprises, that even the simplest systems, a bubble in water, can exhibit behaviors we don't fully understand, that there are still frontiers of knowledge, still questions without answers. And maybe that's the real lesson here. Not the specific mechanism of how sound creates light, but the broader truth that we don't know everything, that physics, for all its power and precision, is still a work in progress, that there's still wonder to be found in the darkness, because at the end of the day, that's what science is. It's the act of looking into the unknown and trying to understand, of finding something that shouldn't be possible and asking, why? How? What does this mean? Sonoluminescence is a reminder that the world is stranger than we imagine, more complex, more beautiful, and that a bubble collapsing in the dark can teach us something profound about the nature of reality itself. If that's not magic, actual magic, the kind that doesn't need wands or spells, then I don't know what is. Thanks for watching. If you want to dive deeper into this topic, I'll leave some links in the description to scientific papers, amateur projects, and videos of sonoluminescence in action. And if you try building your own setup, please be careful with high-voltage equipment and ultrasonic transducers. Safety first. Until next time, keep questioning, keep exploring, and never stop being amazed by the universe, because it will never stop being amazing.